have the next presentation, which is given by Minu, talking about the load deformation behavior of concrete tension ties with Weft-Knitted Textile Reinforcement, very interesting subject as well. And she is working at the university in Zurich, ETHS, with Professor Kaufmann. Please, the floor is yours. Please start with your presentation.
Thank you, Mr. Chairman. My name is Minu Lee, and I welcome you to my presentation on our paper on load deformation behavior of concrete tension ties with Weft-Knitted Textile Reinforcement, with co-authors Dr. Jaime Mata-Falcón and Professor Dr. Walter Kaufmann, who is the supervisor for my doctoral studies on the topic of concrete structures with integrated flexible formworks, which we have been working on since 2018. We are from the Institute of Structural Engineering at ETH Zurich, and this research project is funded by the National Center of Competence in Research, Digital Fabrication. I will first give a short overview of the PhD project in general and our motivation to perform this research, which leads eventually to the approach of an integrated stay-in-place formwork and reinforcement system. Then I will talk about the experimental campaign on Weft-Knitted textile reinforced concrete elements in uniaxial tension, which is the main topic of this paper. In the end, I will give some conclusions and an outlook on the further steps of my research. So there is a continuously increasing demand from architecture for complex shapes due to the possibilities arising from digital design tools. These require bespoke solutions in construction, as we can see, for instance, in the EPFL Rolex Learning Center in Lausanne. The construction of the doubly curved concrete shell required a wooden formwork resting on a temporary scaffolding that we can see in the middle picture. But since the geometry was unique, there was no possibility of reusing the formwork elements, and therefore it led to a high amount of waste. And this kind of very short life cycle of formworks can be found actually in many of today's new structures. Flexible formworks have already been identified as possible solutions for complex geometries. A very promising approach is the Nitrite Technology, developed by the Block Research Group and the Institute for Building Materials at ETH Zurich. And this research was mostly led by Dr. Mariana Popescu and Dr. Lex Reiter. This technology specifically makes use of weft-knitted textiles, which enable doubly curved surfaces and spatial features in the textile without the need of stitching multiple patches together, unlike woven fabrics that only allow for single curved surfaces. The construction concept can be seen on the left side. The fabric here, yellow, is tension in a temporary, or in this case, a permanent support structure. And in this example, bending active rods were integrated in the textile to actively shape it as an arch. Then, on the tension textile, a thin layer of fast-setting high-strength cement paste is applied to guarantee form stability during concrete casting. In the top right corner, you can see the flexible rods. Actually, if you can see the pointer forming this arch. And also you can see that with the very thin layer of cement paste, you can create a very slender formwork system. And of course, also the corrugated shape of the arch helped to reduce deformations. Then also larger structures were then realized, such as the Knit Candela Pavilion that covered an area of 50 square meters. The Weft-Knitted textile enabled a ribbed wafer shell with integrated cables that were tensioned in an external scaffolding frame here on the left picture. And in the final state, you can nicely see the concrete structure on the outside, but also the stay-in-place textile on the inside, which also offers some design potential. For the manufacturing of these textiles, a CNC double bed knitting machine is used. And this basically can create two layers of textiles that can just run parallel to each other, which can be seen here. But by implementing connections between the two layers, for example here, it allows a great variety of geometries and features that can be used for the definition of new feasible formwork and cross-section shapes. Normally, the formwork would serve as a support bottom layer, as depicted in this picture here, where it's just on the bottom. In the Nick Candela, for instance, pockets were implemented and then inflated with balloons, which are these yellow bubbles, to create a ripped cross-section that significantly saved weight and therefore gray energy. Or you could have connectors with different length to create a cross-section with varying thickness, as can be seen here if you have a bottom and a top layer of textile that you fill up with concrete. But then also linear members are feasible. Here, if you connect two layers of textile along two linear paths, a channel is created, which can be inflated by concrete pressure from the inside then to create this circular cross-section. And then furthermore, shaping elements such as cables or bending active rods could be used to define the vertices of a cross-section with partially straight surfaces as shown here. So this looks very conceptual. Here are some, sorry, slide doesn't, oh yeah. So here you can see some actual applications or examples. On the left side, a bit more detailed picture of the ripped waffle shell from the Nick Candela pavilion, where you can see that really this ribbed structure, and then also the cable net which runs through the ribs. In the middle, you can see that you can also create folded ribs that additionally stabilize the formwork. And then on the right side, an example of these inflated concrete tubes where we just filled up this space between the textile, and it really created this tubular frame. But what about reinforcement? The placing of the reinforcement in concrete structures with complex geometry is still a major challenge. And conventional steel reinforcing bars require a lot of manual labor, and complex geometries have smaller tolerances in placing of the rebars. And also logistics are more complicated due to the more specific reinforcement layout. Furthermore, durability is a limiting factor for slenderness, since we have to guarantee a minimum concrete cover for protection against corrosion. Therefore, the objective of this doctoral dissertation is to develop an integrated formwork and reinforcement system, which keeps the advantages offered by the Nitrite technology. Foremost, a fast construction process, low waste for scaffolding and formworks, and the minimum amount of temporary support elements. The reinforcement that we develop shall guarantee an efficient use of materials, and of course, structural safety and post-cracking behavior of the concrete composite. Therefore, we did a revision of multiple existing reinforcement strategies that are being used in construction, from stay-in-place formworks such as steel sheets, conventional textile reinforcement, linear reinforcing bars, and fiber reinforced concrete. But to meet all the defined requirements, we came to the conclusion that a combined solution of multiple reinforcement types would be most promising. Further results of this conceptual study can be found in our paper titled Potential Approaches for Reinforcing Complex Concrete Structures with Integrated Flexible Formwork that we presented at the RILEM Digital Concrete Conference in July this year. One of the identified approaches from this study is a stay-in-place textile reinforcement system. Since the textile is already there as formwork, why not use it as reinforcement in the final state by utilizing high-strength fibrous materials? In this study, we distinguished between textiles where the high-strength material was used directly as yarn in the knitted fabric, as we can see on the left side. And on the other hand, the knitting machine also allows the integration of straight inlays within the base fabric. On the right side, you can see the white glass fiber rovings are just held by a black non-structural acrylic yarn. To study the structural performance of this non-standard reinforcement, we conducted some experimental investigations with uniaxial tension tests on flat concrete sheets to assess the load deformation behavior but also the crack kinematics, where we use digital image correlation-based measurements. The specimens had a thickness between 12 and 60 millimeters, and they all had one single layer of coated textile in the middle of the cross-section. The test setup can be seen in the middle, where the specimen were clamped in plates and then attached with hinged hinge boundary conditions to the testing machine here. Here you can also see the two cameras that we used for the digital image correlation. We had various parameters that we wanted to study. The CNC knitting machine allows an endless spectrum of different knitting patterns depending on the sequence of needles that you activate to create the loops that will form the textile. In this study, we looked at 4 different knitting patterns. In 3 of them, the 3 on the left side, ABC, we used the high-strength aramid yarns directly as knitting yarn to create the textile. And depending on the loop structure, it is possible to create different properties for the stretchiness or the density of the fabric. For instance, the patterns 1-on-1 and 2-on-2 here on the left side look very similar, but the interlock pattern here, figure C, is much denser. Additionally, it is also possible to integrate straight rovings into the textile, as can be seen as thick yellow yarns here on the far right side. So after looking at different knitting patterns, there were also 3 different fiber materials that we tested: aramid, carbon, and glass fibers. They all have a high strength between 2,700 megapascal and 4,300 megapascal. This is in respect to the filament strength, not the roving strength, and moderate to high elasticity modulus. For the directly knitted reinforcement, only aramid fibers were used, since these were the only ones that could be knitted. Carbon and glass fiber rovings are much more brittle and sensitive to lateral loading, and they therefore do not allow for a small bending radii. So they can even be broken by hand when you fold them sharply in. But in the reinforcement patterns with straight inlays, all 3 materials were examined. Okay, to eventually work as a formwork and reinforcement system, the textile have to be coated to create a closed surface where the concrete can be poured onto. We had a look at 2 different coating types, one being a fast-setting, highly fluid cement paste, which had been used in the initial applications of the Nitrite Technology, and on the other hand, a low viscous epoxy resin, which is more commonly used as impregnation of conventional textile reinforcement. Lastly, we also introduced some spatial features in form of ribs in some specimens. Since the surface is quite flat after coating and the concrete is not able to flow through it due to the closed surface, as we can see on the left image, we want to improve the mechanical connection between reinforcement and concrete by creating these bond ribs. They are formed by folding the textile and closing the resulting loop, as is schematically shown in the top right corner. This feature could also be automatically manufactured in the knitting machine. So here's the sequence of production. Very shortly, textiles were tensioned in a wooden frame, then coated with either cement paste or epoxy, and after hardening, embedded in a fine-grained concrete matrix with 5 millimeter on bottom and 5 millimeter on top of the reinforcement. And the specimens were cast on a shaking table to minimize any air voids. For each individual configuration of knitting pattern, fiber material, coating, and bond ribs, we produced 2 specimens. So coming to the results, in this slide, we can see the load deformation behavior for all specimens with directly knitted reinforcement. Due to the knitted process, the structural behavior also depends on the direction of loading, which is called warp, and weft, which refers to the direction of production. Although we could observe a hardening behavior for certain configurations, as we can see here, after cracking, the failure modes of the specimens were rather messy. There would be either local failure in the knitted textile, creating big holes, or excessive swelling of concrete cover. And some specimens also failed shortly after cracking due to low amount of reinforcement content, as we can see in the bottom left corner. Okay, so what we could see from these results is that generally the utilization of the textile strength when compared to the filament strength was very low, and not even 30% could be reached. This comes from the interlock structure of the knitted textiles, where the loops introduce high lateral stresses on the yarn, and which significantly reduce strength. Furthermore, the deformations were very large since the textile introduces a stretchiness which exhibits a stiffness that is a magnitude lower than the fiber material. And therefore, the reinforcement with straight inlays was hoped to perform better since the rovings are aligned to the direction of loading. So here, looking at the stress-strain relationship for the knitting patterns with straight inlays, 3 different materials, aramid, carbon fiber, and glass fiber, and 2 different coatings, cement paste and epoxy. And we can see that the textile stresses reach much higher values of utilization of around 60 to 70%. But the rovings still do not reach the full filament strength. And in textile reinforcement, this has usually 2 main reasons, which have been reported in literature. One is that the stress distribution in a roving is normally inhomogeneous, leading to that we cannot exploit the full strength of the rovings. Another reason is that deviation forces on the crack edges reduce the tensile strength since they introduce highly concentrated lateral loads. There were generally 2 different types of failure. Most of the specimens exhibited a complete rupture of rovings and brittle failure without prior notice, the ones with the blue frame. However, carbon and glass fiber rovings coated with cement paste failed shortly after cracking, and especially the glass fiber rovings here, they showed a distinct softening behavior, which comes actually from a pull-out mechanism where only the outer fiber breaks and the fiber core is pulled out. And this normally occurs due to insufficient penetration of the coating into the roving, and we can see that this type of failure did not happen with epoxy coating, and all these specimens here exhibited hardening, good utilization of strength. So last points to these experiments: in all specimens with hardening behavior, a clear effect of tension stiffening could be observed. That means the mean strains were lower when compared to the bare textile, here denoted as green line, the load deformation plots. And due to the interaction of reinforcement and concrete, part of the load between cracks is taken by the concrete, reducing the strains in the reinforcement. And if we assume a constant bond-slip relationship, the tension cord model developed by Professor Marty can be used, and this leads to the possibility to back-calculate the bond shear stresses with very few parameters. Currently, we're having a closer look at the crack kinematics using the strain and displacement field from the digital image correlation. We can determine the cracking pattern and crack kinematics using the automatic crack detection and measurement software that was developed at our chair by Nicola Gheri and Jaime Mata Falcon. And this serves as an estimation of the average crack spacing and also for measurements of the crack width, as we can see on the right side. So now coming to the conclusions, in knitted textiles with high strength fibrous materials, the ultimate strength of the roving is significantly reduced due to the interlock structure of the yarns and their vulnerability to lateral loading. The integration of straight rovings helped both in strength and stiffness, although it really depends on the type of coating. So with cement paste, the glass and carbon fibers failed shortly after cracking, but with epoxy resin, we could improve both strength and stiffness. And at the moment, as we said, we're looking at the further analysis of the crack kinematics. We also started to apply the findings to bending tests. We also want to have a look at hybrid reinforcement systems using knitted textiles and short fibers, for instance, to improve deformation capacity. And eventually, of course, we want to exploit the potential of knitted textile for doubly curved elements, where we, for instance, can align inlays to the direction of principal stresses. Our thanks to our collaborators, not only from our group, but also from the Block Research Group and the Institute for Building Materials, and also acknowledgement to the funders of this project, the National Center of Competence in Research, Digital Fabrication, and the Swiss National Science Foundation. And I thank you for the attention, and I apologize for the technical issues. Thank you.
Well, thank you very much for this very nice presentation. You gave a very good overview, even though you had some problems with the presentation itself for technical reasons, and so running a little bit out of time, but nevertheless, it was really very, very interesting. And with nicely made slides. And personally, I have to be honest, I learned a lot about the knitting technology and the knitting patterns and its interaction with the behavior, things which I hadn't heard in these details before. So you are, in my opinion, the right way to do a PhD, an excellent PhD work. But nevertheless, there will be some questions. I first start with things which I had in mind when I observed your presentation. Firstly, the cover is not a decisive factor in view of durability, but has a little effect on the mechanical behavior. If I understood right, it is just 5 millimeters?
Yes, yeah, that's correct.
5 millimeter, okay.
Yeah. Independent
of the kind of knitting.
Yes, so it was always 5 millimeters. We designed the reinforcement that the reinforcement ratio would be in a similar range for all configurations.
Okay, then thank you. Another point was to understand your diagrams on the forced deformation behavior fully. It would be helpful for me really to see which are the differences in the matrices. You have the cement paste, what strengths you have in the cement paste, what modulus of elasticity, and you have, on the other hand, the epoxies. No? Can you just give an explanation on that?
So I think the biggest difference in the cement paste and the epoxy resin for the coating or impregnation of fibers is that also already from visual inspection of the broken fibers after we had tested, we could see that the cement paste is really just a coating that is on the outside layers of the rovings and does not fully penetrate into the rovings, and therefore the stress transfer within those inlays or those yarns really depended on interfiber friction, which is quite low. And in the rovings with epoxy, where it really was possible to go into the full cross-section of the roving, we believe that the stress distribution within the roving was much more homogeneous, and therefore also like higher stresses could be reached, and foremost also higher elasticity moduli. So unfortunately, we only have only one direct comparison between the cement paste and the epoxy here on the left side with the Aramid fibers, because the other ones failed already after cracking. And we can see that we actually reach a much higher elasticity modulus for the epoxy coated fibers than with the cement paste coated fibers.
Okay, thank you very much. This gives for me a good explanation for the different kinds of stress deformation behavior. Nevertheless, there remains, so first, maybe if you try in the future also with cement paste with a lower viscosity, there is possible to develop a very low viscous cement paste, which has very good adhesion behavior. So might be you can approach a little bit more the epoxy results if you do it with a different kind of cement paste. The other point, which is surprising, if just looking to the cement paste, that we have such a pronounced decrease in the maximum load between the aramid and the glass fiber. because the strength of the material, the difference is, let's say, 30%, but here we have a factor of nearly 3 or 2.5. What's the reason for that?
So with the outermid fibers, they're much less sensitive to lateral loading.
Okay.
if you handle the fiber materials or the direct roving materials, it is already from taking them into hand. You can see that with outermid fibers, you can actually make knots or really bend them or fold them with a bending angle of 180 degrees, and more or less nothing happens with them. But the glass fiber, they really just break. If you take them into hand, you make a knot into it, the knot will not hold, but it will just break eventually. And therefore, for the glass fiber rovings, once this crack forms, then you really get this deviation at the crack edge, which will just like cut through the glass fiber. And since the cement paste could not penetrate into the roving, it can also not protect the fibers which are in the core of the roving, and therefore they just broke prematurely.
Okay. Thank you very much. Clear explanation for me for this pronounced difference which can be observed. This is not really a material behavior or a composite behavior, but it's some kind of an artificial effect, no? That you have the lateral weaknesses of the glass fibers. That's right?
Yes. Yeah.
Okay, thank you very much for your answers on my questions. I see there are other questions in the chat, and I have to look. What do you mean by blended Portland cement in your paper?
Okay. This is coming from our colleagues from the Institute for Building Materials. I'm a bit afraid that I cannot give too many details on the mix design, because this is by courtesy of the chair of physical chemistry in building materials, and unfortunately they have not yet published the results on the specific mix design in cement paste and concrete matrix that we used. Therefore, I cannot comment too much on it. In this case, it was a standard Portland cement, CEM1, and there were some additional particles that we mixed with it. But I'm afraid, and I'm sorry that I cannot at the moment share more information on this. But I hope they will follow up with a publication on that matter.
Okay, thank you. We understand this point quite well. Well, I think we are at the end of your presentation. Again, thank you very much for a very nice presentation, and good luck for your future. And also thank you very much for the good answers you gave on the questions.